Hi there, I'm Steve Cunnington and I'm a postdoc from the University of Manchester. And today I'm going to be talking to you about how we can use radio telescopes like the MeerKAT telescope shown here, which is the precursor to the Square Kilometre Array, how we can use them to probe ultra-large scales in cosmology, which are radio wavelengths, using a process called 21 centimeter intensity mapping. So to begin with, let me explain what intensity mapping is. So this slide here is showing how we would conventionally probe large-scale cosmic structure. What we want to do is peer beyond our own galaxy, shown here, and look to record matter fluctuations in the dark matter field. Now, because we obviously can't see the dark matter, we have to use some traces of that. The most conventional approach is to use galaxy surveys using optical wavelengths or near optical wavelength telescopes to record as many galaxy positions as we can in 3 dimensions. And if you sufficiently get enough of them, that should sufficiently sample the underlying matter density field. So then you can do things like 2-point clustering statistics on these galaxy fields, and then you're indirectly probing the underlying matter density field. So this works really well, but if you want to scale it up to very large volumes and go to deep redshifts, this starts to become very challenging just because the number of galaxies that you need to detect becomes very large. So intensity mapping is this idea of relaxing this approach of resolving individual galaxies and instead just recording the combined unresolved emission coming from all emitters at a particular frequency coming from a particular line feature. The most common case of this, arguably, is coming from 21 centimeter intensity mapping. 21 centimeter line comes from neutral hydrogen gas. So we use radio telescopes to detect this. So the radio telescopes scan the sky very rapidly, recording all of the emission coming from neutral hydrogen. And then the idea is you build up these intensity maps where you get a particular large blob. You don't care how many galaxies are now contributing to that blob, but you just know there's a lot of dense structure behind it. So you can play the same game and do your 2-point clustering statistics on this intensity field, and then you're indirectly probing the underlying large-scale cosmic structure. So this is quite a quick animation just to confirm how this process works. So you have all the galaxies distributed out, tracing some cosmic web structure. Inside the majority of these galaxies will be contained this neutral hydrogen gas. It's contained within about 95% of all the halos. This neutral hydrogen gas will spontaneously emit these 21 centimeter photons. They stream across the universe, getting redshifted along the way, and this is what we try to capture with our radio telescopes. And then we scan the sky very rapidly, building up these maps, these intensity maps of 21 centimeter emission. Okay, so why bother doing this? Why not just stick to doing galaxy surveys? So first of all, the intensity mapping technique, as you may have guessed, it's much better suited to doing collecting very, very large volumes of sky. So in principle, it'd be better suited to probing what we call ultra-large scales that span these very large volumes. Now, the reason this is interesting to do is because on these ultra-large scales, shown by this cartoon power spectrum here, at very small k, where the large scales live, there can potentially be lots of signs of new physics here on these scales, which we haven't really had the chance to sufficiently probe yet with current surveys. So there'll be things like primordial non-Gaussianity here, which is a window into how inflation works, will be on these scales, tests of relativistic effects. Also, all the modes on these scales are very linear. So linear models work very well on these scales. Whereas going to small k, you have complicated astrophysical effects start to dominate, and you need some quite complex nonlinear models for that. The other advantage is that the 21 centimeter line extends to very high redshift. In principle, it's present all the way through the timeline of the universe, right up to recombination. So galaxy surveys probably struggle to go beyond redshift of about 3. So when we want to go beyond this, 21 centimeter intensity mapping, it will probably be the answer. So it's naturally suited to that. You also get the possibility of having some nice multi-tracer options. So this is the idea of combining 21 centimeter emission with optical galaxy surveys. They're both different traces of the underlying dark matter density field. So if you combine them, you can get some nice cancellation of cosmic variance, which is what the multi-tracer technique does. So that should improve your error budget, especially on large scales where cosmic variance will start to dominate. Related to this is the idea of combining these two different probes. They're both using different instruments. An optical experiment, an optical telescope is very different from a radio telescope. They'll have completely different systematics. So when you combine them, those systematics will drop out. and they'll no longer bias any measurement. So what experiments are going to be doing intensity mapping? There'll be a number of them, which I'm not going to try to list them all. So in this talk, I'm just going to be focusing on the Square Kilometre Array Observatory, so the SKA, and also its precursor MeerKAT. So the SKA it comes in these two components. There's the SKA mid, which is looking at mid frequencies. That's slightly lower redshifts, redshift of 0 to 3 roughly. And then there's also the SKA low, which is a component based in Western Australia, and that's looking at lower frequencies, so that'll be higher redshift. So that'll typically be looking at things like cosmic dawn, the epoch of reionization. So for this talk, I'm really looking at the late universe large-scale structure, so I'll be focusing on SK mid. But there's all this different science that SK will be doing, but it has got a big commitment to do large-scale cosmology and dark energy. So for that, it will really be wanting to do a large-scale intensity mapping survey like I'm discussing here. So here's a quick flash of the timeline for the Square Kilometre Array. It's under construction now. We have 4 dishes already on site in the Karoo Desert for SKA mid. And it will continue to be, this array will continue to be added to. We'll reach about 200 dishes within the next 3 or 4 years. But fortunately, we don't have to wait this long to start doing intensity mapping with this kind of instrument, because we already have its precursor, MeerKAT. That's already on site. It's already been built. It celebrated its 5th birthday earlier this year. So it's already leading the way in many areas of radio astronomy, and also in cosmology for doing radio intensity mapping as well. So MeerKAT it's 64 dishes currently, so it's about a third of the size of the final SKA mid. And it has these 2 wave bands that we can observe in, which correspond to these redshifts here. And here's a picture of MeerKAT in its site in the Karoo Desert in South Africa. So I'm a part of the collaboration known as MeerKLASS, which is the MeerKAT Large Area Synoptic Survey. So what we're trying to do in MeerKLASS is do exactly as I've discussed, use intensity mapping to do a very large area, large volume survey. Now, the way we do this, in order to get the field of views that we require to get a large area, we can't use MeerKAT as an interferometer, as it's primarily designed to do. That's why it's an array of dishes. What we have to do instead is use this technique called single dish intensity mapping. So we just use it as a collection of 64 individually scanning telescopes, but they're all pointing at the same point. So really, for what the nice advantage of this, 1 night's observation corresponds to 64 nights of observation straight away. So we've already done several pilot surveys using this technique, but we'll continue doing this. And in the pre-SK era, so we'll just keep using MeerKAT to do this intensity mapping. We think we'll get to about 10,000 square degrees. That'll be within the next 3 years or so. And observations for that have already begun. So we're already started doing this 10,000 square degree survey. Right, so there's a few challenges for 21cm intensity mapping, which I haven't mentioned yet. So with this quite novel technique of observing the sky, the way you're just scanning and recording all emission instant on your telescope, you're not just going to capture the cosmological signal that we're interested in. Unfortunately, you're also going to get all these other contributing factors, and pretty much all of them dominate the cosmological H1. So foregrounds are probably the most dominant, and also the most consistent as well. They're always there. So these come mostly from within our own galaxy, things like synchrotron radiation from the Milky Way. That can be about 3 or 4 orders of magnitude brighter than the cosmological H1. There's also human-made radio frequency interference, RFI. So even though MeerKAT's in one of the most radio quiet regions in the world, we still can detect mobile phone masts about 50 kilometers away, because it's such a sensitive instrument. So this is something we need to understand and contain and remove from the data so it doesn't bias the measurements. Then there's also instrumental effects coming from things like the noise and also the beam of the telescope too, which we need to understand and control. So we're really starting to overcome some of these challenges. We're doing that with 2 approaches. There's a simulations-based approach and also with empirically with data. So I'll talk about the data side in a second, but just to highlight a couple of simulation-based studies that we've recently done. So the first one is on the left, focused on this idea of foreground cleaning. These very bright foregrounds we need to remove from the observations to access the cosmological H1. Now, we're very good at doing that now. There's been a lot of work that goes into that. The real challenge is understanding exactly what impact that has on the underlying cosmology, the underlying cosmological H1 signal. So when you strip away these foregrounds, you typically get some signal loss and distortion to that underlying signal. So that can affect your final power spectrum measurement, for example. So in this study, what we looked at exactly this problem, and we were able to show that you can reconstruct this signal loss with a process of mock signal injection into your observations. And what's really nice about this, it turned out to be quite a model independent process too. We did quite an extreme test of this where we assumed the true underlying cosmology had an unphysical signal of FNL equals to 100. And then in our fiducial cosmology used for the mock signal injection, we assumed FNL was equal to 0. And what was really nice is that we were still able to recover the correct fiducial cosmology of FNL equals to 100, shown by the black dashed line. The blue data points are that reconstruction. So this is really encouraging for future precision cosmology applications where we need to get sub% accuracy and not necessarily rely too much on fiducial cosmology assumptions. And also on the right, we're able to, we looked at a different case. This was a study where we looked at this problem of, we receive the observations on the skies, they're in like celestial coordinates. But for doing things like measuring a power spectrum in co-moving units, we need to regrid that into a Cartesian space where we can do a Fourier transform and then measure a power spectrum. Now, this is not a trivial process at all. With galaxy surveys, it's a bit easier because you have point-like galaxies, you can just do a transformation of those coordinates and you're pretty much done. But with our maps, we have these cubic voxels filled with intensities, and we need to resample that onto a Cartesian space. And if you try to do that resampling, you can introduce all these different kinds of distorting effects, which is what we highlighted in this paper. But we showed that these can be overcome. You can model these effects, and the conclusion is essentially that you can model these effects to within like sub% accuracy. So it's certainly good enough for future precision cosmology, as it is with both these cases where we're achieving sub% accuracy. So that's a simulations-based approach. We're also showing empirically now with different pilot surveys that this technique seems to work really well, and we can overcome these challenges. So these results here that I'm showing on this slide it comes from the first pilot survey we did with MeerKLASS. So this was a paper put out last year now. So this was the first pilot survey that we did with MeerKLASS. It was only about 10 hours of data, which is very small compared with what we're now doing with MeerKAT. It covered about 200 square degrees though, so that shows how quickly these observations can scale up. And these observations we got to overlap with an existing spectroscopic galaxy survey, the Wigglesy 11-hour field shown by this footprint here. Now the reason for doing this is because we wanted to see, after doing all these foreground removal processes and this regridding, all this stuff we have to do we still have a cosmological signal within these maps? And the way you do this is by cross-correlating the two fields. And on the right here is showing the cross-correlation power spectrum between these foreground keyed MeerKAT intensity maps and the Wigglesy galaxies. So any hollow points here show negative power, but what you can see is on the at the small k, on the larger scale, so we're more sensitive, we get this very nice positive cross-correlation between the two fields. So this is about a 7.7 sigma cross-correlation. And this is like the first detection of cosmology of its kind using a multi-dish array. So this is 64 dishes, all working independently, combining their maps and then correlating them with a galaxy survey. So this is really what MeerKAT will be relying on for all its future observations, this single dish approach. And also the Square Kilometre Array will be relying on it to do its large-scale cosmology science goals. So on to some more current observations. We're continuing. We've done more pilot surveys since then. This is a more recent one where it's about the same patch size that we've done. So it's still about 200 square degrees, but now we've repeated the observations many more times. So the first one only had about 7 scans of the same patch. This has close to about 40. So it's much deeper observations, hence why we've called it the MeerKLASS deep field. So we're getting some results from that, and these will be put out in a paper soon. We get a nice cross-correlation with another galaxy field that we overlap with. This is a much smaller galaxy field, so it only overlaps with about 25% of the patch. So but we still get a nice correlation with these galaxies. But perhaps more interestingly, what we're now really trying to go for is the autocorrelation within this data. This hasn't been detected yet on these cosmological scales. We have got a detection of or an autocorrelation on smaller scales. That was in fact also using MeerKAT as an interferometer. But with this data, what we really want to try and do is get the first autocorrelation with single dish on cosmological scales. So this is the result we're getting at the minute. It's already what we'd call the lowest upper limits, but we're still about a factor of 2 or 3 away from the black dashed line, which is where we'd expect the power to be. So this is hints that there's still some additive systematics within the data, which we think we understand what some of them are. So some follow-up work is going to really try and address that, and we think we have some techniques to remove those systematics. That should really help in 2 ways, because one, you can just reduce the additive bias that it's causing, and also we'll actually be able to recover a lot of the data that we've had to throw away where these systematic effects were too dominant. So if we can recapture some of that data that we've thrown away, that will just improve our signal to noise and improve this measurement. So that's with some work to come. Okay, and looking ahead even more, this is it's a summary of the observations that we've done with MeerKLASS, so the pilot surveys that we already have, and also what's to come. So I mentioned about this, we think it'll be about 10,000 square degrees that we'll cover in the pre-Square Kilometre Array era. That's shown here by this red contour. It's just an approximate patch that we're going to try and target. So this will all be done in what we call UHF band frequency range, which is given here. That all the previous results I've shown are all in L band. The advantage of going to UHF band are twofold. One, it's a bigger redshift range, so it's potentially better for cosmology. You get bigger volumes. You can also, the other advantage is we think it's much more RFI free in these frequency ranges. With L band, we're very RFI dominated below or above a frequency of about 1,000. Whereas at the UHF band, it's much more RFI free, so we should be able to use much more of the band. We'll have much more data. So as I said, observations for this have already begun. We're mostly focusing on this region here, which members of DESI will recognise as this is where a lot of the DESI Year 1 data is contained. We just about overlap with them, even though we're in the south equator. Yeah, this presents a lot of cross-correlation opportunities with DESI with this data. Okay, so in my final slide, I'm just going to summarize. So yeah, I've presented the case for why probing ultra-large scales can be efficiently done with intensity mapping. So in particular with MeerKLASS data, we're showing empirically that this can be done. There's no hideous showstoppers that we've found yet. And also with simulations, we're showing how a lot of the complicated challenges can be overcome, and we can achieve sub% accuracy despite many of these challenges. And also, as I've just said, we're now beginning observations for a very large, about 10,000 square degrees survey, which have started now and will continue over the next 2 or 3 years. So there's lots of work to be done. So if you're interested in getting involved, please do get in touch. And yeah, I'll stop there. And yeah, thank you for watching.